Hello, my name is Erin and I'm a fourth-year cell molecular bio major.
And I'm Grant. I'm a fourth-year biochemistry major. We are both from the class of 2017.
Today we will show you how to solve practice problem 18 from chapter 5.2 in the Gen Chem workbook. I highly encourage you to pause the video now and attempt the problem on your own, using this video as a guide in case you get stuck. The problem reads, mountain climbers often brew tea by melting snow, which they heat over a stove. Our stove burns butane, C4H10, which has a heat of combustion of negative 2,878 kilojoules per mole. The temperature of snow is initially at negative 20 degrees Celsius, and we need 80 degrees Celsius water to brew tea. Part A asks us, how much heat is needed to turn the snow into a cup of water hot enough to brew tea? To begin the problem, it is important we write down the information given to us and also what we are trying to find. They tell us butane's heat of combustion is negative 2,878 kilojoules per mole. They also tell us the initial temperature of the snow, Ti, which is negative 20 degrees Celsius. The final temperature, Tf, we need to reach to brew the tea is 80 degrees Celsius. The volume, V, of water we are trying to heat is 237 milliliters. In part A, we are trying to find Q, which is the heat required for this process.
Okay guys, since this is a phase change problem, we need to draw a heating curve. Heating curves look something like this. They have heat on the x-axis, the unit here is joules, and they have temperature on the y-axis, and our unit here is going to be in degrees Celsius. For our problem, we're starting at minus 20 degrees Celsius, and we're ending up at 80 degrees Celsius. So initially, our ice is going to heat up from minus 20 to 0. Once it reaches 0, it undergoes a phase change, so it's still going to absorb heat, but its temperature is going to stay the same. Then once all the ice has melted into water, the water is going to heat up from 0 to 80 degrees Celsius. So we can kind of split this graph up into 3 different portions, which I'm going to do right now, with these very straight lines. Portion 1, 2, and 3. Portion 1 corresponds to the ice heating up from minus 20 to 0. Portion 2 corresponds to the phase change. And portion 3 corresponds to water heating up from 0 to 80 degrees Celsius. I'm going to move on to talk about the equations now. Please rewind the video and pause if you need to reference this graph. We will now calculate the heat required for each portion of the graph and sum up the heats to get the total heat. The first equation we'll need to use needs to describe a temperature change because we're talking about ice heating up. We'll go ahead and use Q equals mc delta T. Q is the heat in joules. M is the mass, specifically of the ice. This is going to be in grams. C is the specific heat. This will be for the ice, and it's something you'll either be given or need to look up. I went ahead and looked it up online and found it to be 2.05 joules per gram degrees Celsius. Specific heat simply describes how much energy you need to put in to heat something up. So in this case, it takes 2.05 joules to heat up 1 gram of ice by 1 degree Celsius. And finally, delta T is the temp change. I was able to look up the specific heat, but we'll need to go ahead and calculate out the mass and the temperature change before we can calculate Q. The mass will come from the volume of water. We can take the volume of water, 237 milliliters, and multiply it by the density of water, 1 gram over 1 milliliter. This will give us out 237 grams. Not too bad, right? To calculate the temperature change, this is also not too difficult. You take the final temperature and you subtract out the initial temperature. In our case, we have 0 degrees Celsius minus negative 20 degrees Celsius to give us 20 degrees Celsius for our temperature change. Let's now plug what we know into our equation and get out the heat for the first part of the graph. Q1 is going to be the mass of the ice times the specific heat of the ice times the temperature change. The degrees Celsius will cancel and the grams will cancel. And after calculating it all out, you get that your heat required for this step is 9,717 joules. For the next step, the phase change, we'll need to use a different equation. For this step, we'll use Q equals N delta H, where N equals the number of moles of water delta H equals the enthalpy of fusion for water. So the enthalpy of fusion is something that you'll either be given or you'll have to look up. In this case, I looked it up and I found that it was 6.02 kilojoules per mole. This means that it takes 6.02 kilojoules to fully melt 1 mole of ice. And Q, as always, is the heat required in joules. So we have the enthalpy of fusion, we looked that up. We do not have the moles of ice. We'll need to calculate that out. The moles of ice will just come from the grams, 237, and we'll divide by the molecular weight of water, since we're working with frozen water here. After calculating everything out, you'll get that the moles are 13.2, which we will use in the next step. Now that we have the moles, we can go ahead and calculate Q. Q2 is going to be the moles times the enthalpy of fusion. The moles cancel out, and you get your answer to be in kilojoules, 79.464. Do a quick conversion, and we can get this into joules. We have 1,000 joules in every 1 kilojoule, and you get 79,464 joules. For Q3, we'll solve it very much the same as we did Q1. Since we're talking about a temperature change, water heating up from 0 degrees Celsius to 80, we're going to use Q equals MC delta T. Our mass is going to be the same, 237 grams, nothing's changed. The specific heat this time is different. It's the specific heat for water, not for ice. I went ahead and looked this up online. You'll be given to it on your test. It's 4.18 joules over grams degrees Celsius. The temperature change, I'll go ahead and calculate that out right now in the exact same way. We take the final temperature, 80 degrees Celsius, minus the initial temperature, 0 degrees Celsius, to give us a full temperature change of 80 degrees. We have our 3 variables, so let's just go ahead and calculate Q3. 237 grams times 4.184 joules over grams degrees Celsius, and then the temperature change, 80 degrees Celsius. Again, the degrees Celsius cancel, the grams cancel, and after doing all the calculations, you get Q3 to be 79,253 joules. Now that we've calculated all 3 Qs, calculating the total Q is as easy as adding them up. Q total is equal to Q1 plus Q2 plus Q3, which is simply just the Q from each step. To quickly punch this out, Q1 was 9,717 joules, Q2 79,464 joules, and Q3 finally was 79,253 joules. And when you add all these up, you get Q total is equal to 168,434 joules. And through a quick conversion, you'll get that the total Q for this process is 168.4 kilojoules. This is the solution to part A. We'll now move on to part B.
Now that we have our Q, which is 168.4 kilojoules, we can use the heat of combustion to find the moles of butane, and from that, we can get the mass using molar mass. To find N, our moles, we need to divide negative 168.4 kilojoules, which is the Q, by negative 2,787 kilojoules per mole, which is our heat of combustion. It is important to note that the heat we calculated in part A is positive because it's being absorbed by the water. The heat we're plugging in here is negative because it is being released by the butane. Doing this calculation, we find that N is equal to 0.0585 moles. We multiply the moles, 0.0585, by the molar mass of butane, 58.12 grams per mole, which you can find either by the periodic table or looking it up online. Calculating this, we find the answer is 3.4 grams, which means we need 3.4 grams of butane to prepare 1 cup of tea. This is the solution to part B. Now we have completed the problem. Thank you all for watching.
And have a great time in all your chemistry adventures.